Climate is not the same as weather. Weather changes from hour to hour, day to day, while climate reflects the overall state of Earth's atmosphere and oceans over decades and centuries. It is the combined behavior of winds, rainfall, temperature, and ocean circulation, interconnected components operating within one unified system. This system is shaped by the sun's energy and by the continuous motion of our planet. Every ray of sunlight, every shift in wind, and every pulse of the ocean contributes to the climate we experience. Yet this seemingly stable system is now changing, faster than at any point in human history. Today, we will explore how Earth's climate system functions, why it is changing, and what these changes mean for the future of our planet. What is the climate system? Earth's climate system is composed of 5 interconnected components: the atmosphere, the oceans, the biosphere, the cryosphere, and the continents. Each part has a distinct function, yet all depend on one another at every scale. The atmosphere surrounds the planet like a vast insulating blanket, absorbing, retaining, and transporting energy. The oceans store enormous amounts of heat and redistribute it through currents that travel thousands of kilometers. The biosphere, from forests and grasslands to microscopic organisms, drives the carbon and water cycles, directly influencing climate regulation. Ice and snow reflect sunlight, helping maintain a stable planetary temperature, and the continents absorb and release heat, shaping wind patterns, ocean circulation, and weather systems. All these components operate using energy received from the sun. As Earth's surface absorbs sunlight, it warms and transfers heat into the atmosphere. The atmosphere carries this heat over great distances, while the oceans store it for long periods. Any change in one component, such as the loss of forests, the melting of ice, or the warming of the ocean, creates feedbacks that ripple through the rest of the system. The global climate, therefore, is the result of countless interactions occurring continuously, from minute movements in the air to deep variations within the ocean. It is a dynamic, interconnected machine shaped by both natural processes and human influence. The sun is the ultimate source of energy for Earth's climate. Every movement of wind, every ocean current, and every temperature difference across the planet originates from solar radiation. However, this energy is not distributed evenly. Near the equator, sunlight strikes Earth almost directly, delivering greater energy to each square meter. Near the poles, the same sunlight spreads over a much larger area and is absorbed far less efficiently. This imbalance between warm and cold regions creates the fundamental forces that drive the global climate system. About 30% of incoming solar radiation is reflected back into space by clouds, bright surfaces, and ice. The remaining 70% is absorbed by land, water, and the atmosphere. As the surface warms, it emits infrared radiation upward. Greenhouse gases trap a portion of this outgoing heat, keeping Earth warmer than it would be without an atmosphere. The balance between energy absorbed and energy radiated back to space determines Earth's overall temperature. Heat absorbed in equatorial regions does not stay there. To maintain balance, Earth must redistribute energy from warm areas to cooler ones. Warm air rises and flows toward higher latitudes, while cooler, denser air sinks and moves toward the equator. The oceans also participate. Warm currents carry heat away from the tropics, while cold currents return from the poles. Together, these processes create a planet-wide circulation system. Without this continuous redistribution, the equator would become unbearably hot while the poles remained perpetually frozen. Earth's climate is, in essence, nature's attempt to maintain equilibrium, balancing heat and cold, absorption and reflection, storage and release of solar energy. The atmosphere, the climate engine. The atmosphere functions as a massive engine that converts solar energy into global circulation. At the equator, warm air rises vigorously, creating towering columns of convection. As this air moves poleward, it cools and sinks around 30 degrees latitude, forming the world's major desert belts. This pattern is known as the Hadley cell, the strongest circulation feature in Earth's atmosphere. Farther from the equator, the Ferrel cell operates in the mid-latitudes, where warmer and colder air masses interact, producing powerful storms and complex weather systems. Near the poles, the polar cell dominates, where cold, dense air sinks and spreads outward. Together, these three circulation cells generate Earth's global wind patterns, the trade winds in the tropics, the westerlies in the mid-latitudes, and high-altitude jet streams that steer storms across continents. Atmospheric circulation shapes rainfall, drought, storm formation, and even the boundaries between forests and deserts. Regions where air rises tend to be wetter, while sinking air produces dryness. Strong and persistent winds over the oceans create waves and drive surface currents. Calm regions lead to stable, quiet seas. The atmosphere also interacts intensively with the ocean. Winds push surface waters, forming major ocean currents, while changes in atmospheric pressure patterns can shift rainfall, alter sea surface temperatures, and trigger events such as El Niño and La Niña. Even small shifts in the jet stream can dramatically change seasonal weather patterns, causing heat waves, cold spells, or prolonged storms. The oceans, Earth's long-term memory. The oceans act as the long-term memory of the climate system because they can store vast amounts of heat over extended periods. While the atmosphere may warm or cool within days, the oceans take years, and sometimes centuries, to adjust. This ability makes the oceans central to determining both present and future climate conditions. Surface currents, driven largely by winds, transport enormous quantities of heat across the globe. The Gulf Stream, for example, carries warm tropical water northward, allowing much of Europe to remain far milder than regions of Canada located at the same latitude. In the Pacific, the Kuroshio Current plays a similar role for Japan and East Asia. Deep ocean currents behave differently, guided by variations in temperature and salinity. Cold and salty waters sink and flow along the ocean floor, traveling thousands of kilometers before rising again. This global conveyor belt, known as thermohaline circulation, connects the world's oceans into a single, unified system that takes centuries to complete one loop. Even small changes in ocean conditions can generate large climate responses. As oceans warm, they expand, contributing to sea level rise. Warmer water can weaken major currents, disrupt weather patterns, and intensify climate events such as El Niño. Because oceans absorb more than 90% of the excess heat trapped by greenhouse gases, the warming we see today will influence climate patterns for decades and centuries. If the atmosphere is the fast, beating heart of the climate system, then the ocean is its deep, steady memory, absorbing change slowly, yet determining the long-term trajectory of Earth's climate. Clouds and water vapor. Clouds and water vapor are among the most sensitive elements of the climate system because they influence both warming and cooling. Water vapor is Earth's most abundant greenhouse gas, effectively trapping heat and amplifying the effects of carbon dioxide and methane. As the surface warms, evaporation increases, adding even more water vapor to the atmosphere and strengthening the greenhouse effect. Clouds behave in more complex ways. Low, thick clouds tend to reflect large amounts of sunlight back to space, contributing to surface cooling. High, thin clouds, however, allow sunlight to pass through but trap heat escaping from Earth's surface, producing a warming effect. The balance between these cloud types, and how they shift with global warming, is one of the most important uncertainties in climate science. Even small changes in cloud cover or water vapor concentration can significantly alter Earth's energy balance. Because clouds form and dissipate rapidly, they are difficult to predict. Yet they remain central to understanding how fast and how strongly the climate will respond to continued warming. The decline of ice and snow. Ice and snow act as Earth's natural mirrors, reflecting most sunlight that reaches them. When ice cover is extensive, the planet reflects more energy and stays cooler. But as ice melts, darker land and ocean surfaces are exposed, absorbing more heat and accelerating warming in a self-reinforcing feedback loop. Nowhere is this change more visible than in the Arctic, where summer sea ice has shrunk dramatically over recent decades. This loss alters regional temperatures, wind patterns, and ecosystems. Greenland's ice sheet is losing hundreds of billions of tons of ice each year, while parts of Antarctica are also experiencing persistent ice loss. Melting ice contributes directly to rising sea levels, but it also impacts climate circulation, changes the distribution of heat between the ocean and atmosphere, and disrupts weather patterns far beyond polar regions. The rapid decline of ice is one of the clearest indicators that Earth's climate is undergoing profound and accelerating change. Why the climate is changing. Over the past 150 years, the rapid acceleration of climate change has been driven primarily by human activities. Burning coal, oil, and natural gas releases large amounts of carbon dioxide into the atmosphere. Agriculture and livestock production emit significant quantities of methane. Deforestation reduces Earth's natural ability to absorb carbon, while industrial processes and transportation add further greenhouse gases. Atmospheric carbon dioxide has risen from about 280 parts per million before the Industrial Revolution to more than 420 parts per million today, the highest level in at least 800,000 years. As a result, global temperatures have increased by about 1.2 degrees Celsius. These changes have intensified heat waves, strengthened storms, shifted rainfall patterns, and disrupted ecosystems around the world. Natural factors alone cannot explain the scale and speed of modern warming. Scientific evidence overwhelmingly shows that human influence is the dominant cause of today's climate change. The future of Earth's climate. Earth's climate system is incredibly intricate, yet it is not unchangeable. It responds to every alteration in energy, temperature, and circulation, no matter how small. Today, humanity stands at a crossroads. We can deepen our understanding and safeguard the climate system, or we can witness increasingly severe impacts on water resources, food supplies, ecosystems, and global stability. Climate is not merely a scientific subject. It is the foundation of life, shaping every environment and every society. The future of Earth's climate depends on the choices we make today, choices that will influence generations to come.